So in the front page, I should be able to see it as soon as the streaming is available. Can you please take a look at how his appearance? Because sometimes this screen may be too big. The voice should be fine because I'm using that particular mic that is next to me. Still nothing. So is this slide large enough? And is in a good location. So can I take a look? It looks all right, I think. I think that it is all right. So I just need to find out these videos by myself. So it's okay. Seems not to be able to do so within this short notice. Okay. Now, let's get started for today's lecture. And like I mentioned just before I put the recording and the streaming on, this is our fifth lecture. And as agreed in ground rules, there's supposed to be 6 lectures in total, and then there's planning to be a midterm exam. And I just discussed that I would like to change the plan a little bit, such the way that I will explain all the theoretical matters this week and next week, and then there will be a 7th lecture. And in a 7th lecture, I would like to give you a summary. Kind of like a list of knowledge that you have to have whenever you're entering the midterm exam. And some guidelines, like what actually makes sense to learn, what makes sense to prepare yourself. And I think that this will be very beneficial to you. And we agreed that this is what I can do, so that's the plan. So that's how it goes. Now, there's another reason to have a lecture in 7th week. And that is related to our students that are following the lecture using this online option. These students are entitled as a Jedi student and Mech/Elect students. They will be around in week 42, which is within 2 weeks. So they will be here in the university, and they will do the intensive tutorials during that time. And I'm hoping that, this goes to online participants. I'm hoping that once you're here, you will take this opportunity and come and see this lecture, on live, here in the lecture room. And the lecture room is 2310. It's one of the big lecture rooms we have. Hopefully you're here just to see how it appears, how the recordings actually are. And I think it's going to be fun for you too. Now, this affects to you too, guys. I mean that it affects to all of us. Because in week 42, which is a Monday, October 14th, there is no guided tutorials for other students. So tutorials are for Jedi and Mech/Elect students only. So nothing for you in that particular week, except lectures, of course. Also, the next week after that is a midterm exam week. So there will be no lectures, no guided tutorials. Only action we have is a midterm exam, nothing else. And then once you're coming back, which is week 44, then we will keep on discussing about few matters related to flexible multibody dynamics and multibody dynamics in general. And then we're starting to look at how is that we can make models of different actuators. So that's the plan. But now, let's go and summarize what we discussed last week. And the last week we'll look at how is a kinematic analysis. Now, let me emphasize this. Kinematic analysis is for a system where the number of degrees of freedom is equal to 0. This is the only opportunity to run the kinematic analysis. How come? Well, simply because the kinematic analysis will be carried out by using the information that is in a constraints equation. Nothing else. So that's the only information we need. And now, in order to do that, you have to create something that is called Jacobian matrix, which is something that you can get when you differentiate your constraints with your variables. Your constraints are denoted as a vector C, like you can see in this here. So it's a vector C here, I need to put a drawing. Is this the drawing? No, it's not drawing. How can I put my pen on? Is it now on? No, this is gonna go the big mess. Not that. I need to find it out that in a second. Design. Pen. Where's my pen? Ink. Let's use this. Now it's here. So what I was about to explain is that you have to have your constraints, your vector of constraints, and then once you differentiate that with respect to your variables, and your variables are generalized coordinates, that's how you can build your Jacobian matrix. The equation that I'm pointing out here, this one here, is telling you how is it you can compute the individual component within your Jacobian matrix. And your Jacobian matrix eventually look like the one that is shown here. Dimensions of the Jacobian matrix corresponds your number of constraint equations and number of generalized coordinates. And you can invert the Jacobian matrix, which is exactly what you need to do when you're computing the Newton difference. You know, this inverse is possible only when you have a skew matrix. And that tells you that the only possibility to run the kinematic analysis is that you have 0 degrees of freedom. Okay, this is how you can carry out the kinematic analysis in position level, but we agree that there are 2 other levels that you have to handle. And those are velocity level and acceleration level. You know, they look more involving, I mean, the velocity and acceleration level, but in reality, those steps are much simpler than position level. And the reason being that in velocity and acceleration level, the only thing you need to do is a substitution. So you're substituting your information to this equation. Again, there's not, how come it's keep on disappearing my writing? So I need, where is that I can put my pen on? Here? No, here. How I did it in a previous case? I forgot it already. Where was it? Was it here? No, it wasn't here. So it was design? This one, design or? Ink. Where is it you can see ink? Oh, here. Yeah, that's how I did it. So now, I was about, where was I? Velocity level. Look at me, so I'm getting better, you know, what comes to my memory. My memory is very, you know, strong, but it's a little short. But anyway, so, you know, this is Jacobian matrix that you need to invert it, but, you know, getting velocity is all about the matter of substitution. You substitute your information to these particular locations, that's it. No iterative process, like is the case when you're comparing the position level. The position level, again, is the first step you have to carry out. So that is based on iterative process. Then next one is just the substitution. And the acceleration level, that too is based on substitution only, nothing else. All right, then last week we opened this painful topic, which is related to generalized forces. Now you need to pay attention to me. So you need to take your notes off and listen what I'm saying, because this is now very, very, very important to understand. Because the bad news is that when you were wondering like, oh my God, this generalized external applied forces is such a complicated concept that I'm having a very hard time to understand that. You have to understand it, because the next, what we will do is that we are applying this very same concept to inertial forces. And it will be mathematical nightmare. It will be very involving. So that's why you have to understand the concept already this time. All right? So you're paying your full attention to me. Yes. Okay, let me explain what's the deal with generalized inertial forces. Well, we have situation where the forces are expressed by using global coordinate systems. An example is the force that is showing, in this point here. So I have here externally applied force that is having two components. These two components are forces in global X and global Y coordinate axis, along the global X and Y coordinate axis. Now what I really wanted to do is that I wanted to express my equation of motion by using generalized coordinates. I wanted to have explicit definition of generalized coordinates. Why? Because those are the unknowns. Those are the ones that are telling me the full configuration of my multi-body system. So that's why I wanted to solve it. How can I make it happen? I can make it happen in such the way that I convert these forces to be expressed by using generalized coordinates. Now, my global coordinates are X and Y, right? What are my generalized coordinates? Well, depending how many bodies I have in my system, but if you're just dealing with the one body, then the vector of generalized coordinates consists of three components that are Rx, Ry, and angle theta. Now, what I'm aiming here is that I would like to convert this expression from global coordinates to be expressed by using generalized coordinates. You know what is our objective here? You know what is our mission? Is it clear now?
What is the difference between body coordinates, general coordinates, and...
So now there is so many coordinates that you could completely confuse. So let me repeat the question. So the question was, what's the difference between global coordinates, generalized coordinates, body coordinates? Okay. So global coordinates is global coordinate system that is standing still. That's a coordinate system that is not moving. That is our point of reference. That's where we're going to measure the dynamics. Example is this coordinate system that is attached to rock. So it's not moving anywhere at all, no matter what's happening in our system. That is global coordinate system. In planar case, it consists of two axes that are X and Y, right? Then generalized coordinates are the one that I'm using to express my kinematics. Okay, what is my kinematics? Well, I'm using this equation that you're very much familiar with to express all possible locations in my system. Now, what are the variables that I'm using in my equation? Well, there are components associated to R, which are Rx, Ry, and then there's one more generalized coordinate that is associated to rotation, and the rotation is expressed by using 2x2 rotation matrix. What coordinates is that? That's angle theta. All right? That's it. The body coordinates is non-existing. We're only dealing with two sets of coordinates, global coordinates and generalized coordinates. We do have a body reference coordinate system. The body reference coordinate system, we have vector u bar. Remember, the vector u bar is the one that we are using here, this one here, to define any particle within the boundaries of the body. Is this clear? So it's like, oh my, so it's very clear. So it's very clear. All right? My voice is still loud enough. Maybe I should put the volume up to make this more understandable. Okay, so now you understand the objective we have. So we wanted to express the forces by using generalized coordinates. That's what we really wanted to do. How is that we can make this happen? Well, we can make this happen with help of the concept of virtual work, because we need to have a mapping between two coordinate systems. Those coordinate systems are global coordinates and generalized coordinates. And now there's mathematical magic we're doing can be written like shown here. So let me try to write this with a good handwriting. So delta R, which is associated to virtual displacement of a particle with respect to global coordinate system, because R consists of two components, can be expressed in such the way that is a partial R, partial Q multiplied by delta Q. And this looks like, oh my God, what a mathematical nonsense. So how can it's gonna help my life? But it helps your life, because look what we are after here. So we are after to combine these two coordinate systems that are, again, global coordinates and generalized coordinates. And this mapping we desperately need is described by this partial operation, because R here is a vector, Q here is a vector, partial R, partial Q is a matrix. For a one body is a matrix that consists of 2 rows, 3 columns. What are these columns? Well, those are associated to our tenorized coordinates that again are Rx, Ry, and angle theta. Rows are associated to global coordinate axis X and Y. So here it is. That's our mapping we need. Now, we're going to take this mapping, and with help of that mapping, we're going to convert to our forces to be expressed by using tenorized coordinates. That's how it goes. Now, my advice to you to understand the concept of virtual displacement and virtual work is like exactly like this, mapping. Mapping between one coordinate system to another coordinate system. Combine these two sets, because otherwise this is no go. And it's simply no go because here we have, say, global coordinate system. We have 2 components in our forces. Here we have tenorized coordinates, which is 3. 2, 3 is like this famous banana apples, whatever you wanted to say, they don't match. No match. We have to build the bridge between global and tenorized. So where is the bridge? Partial R, partial Q. So we can call this as a bridge. Miracle maker. Magic matrix. Whatever you want. But you know what it's doing for us? It is mapping global coordinates and tenorized coordinates. Make sense? It's like, I can see like, I don't know how many people we have here, but like 2 are doing like this. Others are like, oh my God, oh, this is painful, painful thing. My advice to you is this, do this, because otherwise I keep on repeating this. And how it comes to your head is like, it's like broken radio. So, is it like, it's like, I don't know, I'm very, very confused. So let's summarize this. Now, what I'm aiming again is to express my forces using generalized coordinates. And how it goes? Well, this is how it goes. So I have my force that is expressed by using global coordinate system. And I'm using this concept of virtual work to do the mapping. Virtual work is force multiplied by displacement in the direction of force. How is that we can express that, mathematically? Well, it's a force multiplied by displacement, and the displacement is very tiny, mathematical. Let's call this as a mathematical tools that we have. Delta R. And now, we know that this delta R can be related to delta Q. So those are the 2 coordinates, global and tenorized. And this relation takes place with help of this partial operation, which is partial R, partial Q. And now when we, looking the details of that mapping matrix, the mapping matrix is having 2 rows, 3 columns, and it can be expressed such the way that, here in a left-hand side of that matrix, I have 2 by 2 identity matrix. What is in the right-hand side of that matrix is a rotation matrix that is differentiated with respect to angle theta, and then multiplied by vector u bar. Okay. Now you do the math. This is how you can express your generalized, your force is expressed by using generalized coordinates. That's what it is. So now, remember last week I asked, what's the role of this matrix? Remember that? There was in-class quiz. I asked, like, what is that matrix is doing for you? So let me ask again. Physical interpretation of matrix, partial R, partial Q, in the case of virtual work. Now, the options are, defines the relationship between the global coordinates and constraints, defines the relationship between the constraints and generalized coordinates, defines the relationship between the global and generalized coordinates, and finally, defines the relationship between external applied forces and constraints. Only one is correct, but which one is correct? Let me take, I can see that Socrative is not on. Hold on. I thought that it was on already, but I need to, are you already logging in? I'm not sure what to do. Can I just go and check it out here? No, I cannot do that. I need to restart this. So that's a good news. So even if you miss, accidentally place an incorrect answer, you have an opportunity to do that again. Sorry about that. Yeah, that's because my computer was about to restart it, and I think that was the reason. I can see that you're coming back. Now select the correct option out of the 4 options. So the only one is correct. But which one is correct? Okay. So while you're doing that, so let me move on. I wanted to repeat the example that I demonstrated to you last week. And this is a case, and I will go and take a look at the Socrative in a second. But I'm thinking that, today the success rate goes up to 80%, 90%, 95%, 99%, 90%. But remember, this was exactly the same question, exactly the same options than in the last Monday. But of course, I remember there's so many stuff to come into your head that you're worried, like, if you're gonna memorize this, something critical like how to walk will coming off from your head. So you need to be careful with that. Okay, so let's take a look at that in a second, but prior to that, let's look at the example. And I wanted to show this example because the next in-class quiz will be related to this. Now, I have here force that is applying in the center of the mass of the body. Again, I need to use this one. So here's my force is expressed in global coordinate axis, and obviously it's a gravity force because it's a gravity constant multiplying by mass of the matrix, and it's applying here. And now I would like to express this by using generalized coordinates. And now look where the body reference coordinate system is located at. So it's located here in one end of the beam-like body. So how can I make this happen? Well, I could do it this in a way that I define the point where the force is applying by using this equation that we are very much familiar with. And then I can differentiate that with respect to my generalized coordinates. And because I'm dealing with the one body only, it will be 3 coordinates. And now this is the one that gives me the mapping that I'm needing. And once multiplying force with this mapping matrix, then that's it. That's going to be my generalized force is expressed in terms of generalized coordinates. But now I'm going to take a little bit of shortcut here. I'm going to use the definition that was provided in a few slides back. And in that definition, this map, oh no, look. going back here, so this definition was provided here. So it was a identity matrix, 2 by 2 identity matrix, and then the final component is you can get by multiplying the rotation matrix that is differentiated with respect to angle theta with vector u bar. Alright, so I'm going to take that shortcut option, and with help of the shortcut, knowing that the vector u bar is having the component L divided by 2 and 0. By substituting that information, my mapping matrix looking like this. So this is transpose of the mapping matrix. So each one of the rows this time, because it's a transpose operation, corresponds to my generalized coordinates. Each one of the columns, again because of the transpose operation, correspond to global coordinates. All right. So I'm gonna use this mapping matrix, and I'm gonna multiply this of my original force with the mapping matrix. And that's going to give me the generalized externally applied forces expressed by using generalized coordinates. Now something interesting is this. The final component that is associated to angle theta. Obviously this is a moment that you can get by computing the level arm of where the force is applying to the distance where the body reference coordinate system is located at. Because look at this, so it's L divided by 2 multiplied by cosine alpha. So now if I go back here, but well, not gonna touch anymore, but it's this level arm that is, as a result, that is applying to angle theta, my third generalized coordinate. Now, to get the better picture of that, I'm gonna show you another example. But prior to that, let me take a look at the in-class quizzes. And then there is gonna be another in-class quiz, which is related to similar kind of question. Maybe too challenging, but I'm still gonna give a shot. So we'll see how it's going to be. Okay, so we have 84 students, 83 already entered the answer. And the success rate will be what? 90. No, that's not that, but it has to be exact number because this is lottery. 89. Okay, others? 82. You know what I'm going to say? 100. Correct, 100. So it's going to be 100. And it's very close to it. Look at this. Look at this. This is amazing because, look, last time I think it was like 50 something, 52 or something. 94, it cannot be higher. I don't think in practice it cannot be any higher than that. And why not? Because, there are online participants that are watching Netflix and then they are hearing, oh, in-class quiz, let me take a look. And then they're going to give a wild shot. And that's it. And that's it. And this is how it's going to be. But it's very good. It's really, really good. I'm honestly a little bit proud of myself. What do you say if we're going to repeat this next Monday? Maybe it's going to work out. Maybe I'm going to do it because, it's quite interesting. This is kind of fundamental of this multi-body dynamics. So let me go back here. Now, based on this first example, I'm going to ask you this. Well, let me put the soccer there on, and then I'm going to ask this. So I have a gravity force that is applying the very same system. It is a very same system. How is going to be the vector of generalized externally applied forces, how that will appear? Now the first thing that is important you to understand is how many components that vector will have. Think about it. How many components that vector will have, because I have one moving body, one force that is applying to it, but really what matters here is that I have one moving body. Think about the number of components you have to have in that force vector. That once you get that correctly, that will eliminate 2 off from from your choices, and only 2 is left. And then you have to think about how is that the force that is showing in a picture will affect to angle theta. What is its moment arm? Once you know that, then you can get it correctly. Is that clear enough? Is it too easy?
But theta doesn't apply to.
What? Theta is what? Well, let me explain the choices. Maybe that's what helps you as well. My choices are here. Vector that consists of 3 components, and these are 0, gravity constant multiplied by mass in minus, and then 0. And then the same component, but this third component is a little different. Then I have here 0 and mass multiplied by gravity constant, and then my final one is 0, and then there's a kind of moment arc. But what is correct? So I'm thinking that even this is difficult, a little bit difficult, but still we're gonna score high in this example. And you can hold on, you don't need to enter your answer if you're not 100% sure about that. Think about it a little while, and let me take another example. And once this example is done, then we can come back to this, and this is supposed to be clear to you. All right? And then, by the way, that's when the fun part will end. Then we're gonna go to that serious business about how is that we can do this same trick, but for inertial forces. And it's made a mess. I can tell you this already, so enjoy when you can, because soon you cannot. All right? So you have fun? I don't think so. But anyway, so let's take a look at this. So let's look at an example, that next example that I have. Hold on, I'm a little lost. Yeah, look at I have this miracle pen. So now I have a triangular shaped body. Again, this is a planar shaped body like always in this class. And I have 2 forces applying in a triangular shaped body. And now it's very important to understand that these forces are applying in global coordinate system. Forces are, let me explain that. So there is a forces are force that is applying with respect to global coordinate axis x and y, and the units are 10 and 10. So these are numerical values that I'm using here. And is applying in a position that is called A. And position of A is a little off from the body reference coordinate system, because the body reference coordinate system is located exactly same place where the revolute joint is located at. All right. Then I have another force that too is expressed in the global coordinate system, is having exactly same numerical values than in the previous case. This though is applying in the position B, and the position B is up here, with the U-bars that are needed to express these 2 points are expressed here. And now I would like you to express these 2 forces in terms of generalized coordinates. So what are the generalized coordinates in this particular case? How many coordinates we have? 3, because everybody needs 3, meaning generalized coordinates, of course. Okay, so it's 3 generalized coordinates. Those are Rx, Ry, and angle theta, right? Okay, so let's go and make this happen. So let's first express this location where the force is applying, and I'm gonna obviously get started with my point A. So this is my point, but then I'm gonna look in the very beginning. So no thinking. I'm gonna just go ahead and use the equation that I'm very much familiar with. So I'm gonna express, how the body reference coordinate system is translated with respect to global coordinate axis. And this is gonna be vector R, and then I'm gonna count the rotation of the body reference coordinate system. That's gonna be my 2 by 2 rotation matrix, And then very mechanically, I'm going to substitute my vector u bar to take this equation. Now this is when things becoming clear to you. Look what I'm going to get. I'm going to get the vector of two components because this expression is in global coordinate axis with respect to global coordinate axis. Now I'm going to, with no further thinking, I'm going to just go ahead and differentiate these two components with respect to my generalized coordinates. And again, those are Rx, Ry, and angle theta. So when I do that, my first equation, when I differentiate this with respect to first Rx, it's going to give me 1. When I differentiate the same equation with respect to Ry, it's 0. And with respect to angle theta, this is what I'm going to get. Yeah, it looks all right. And then I'm going to repeat that for the next component, which is this one. And here's my mapping matrix. Now I'm going to take this mapping matrix and multiply my force with that mapping matrix. It's going to give me a vector of 3 components because I'm having 3 generalized coordinates. Those are 10, 10, and the component that is affecting to my angle theta. Next, I'm going to go over again and repeat this same story, but this time point B. No difference. So let's make it happen. Point P, so I'm going to again take the translation of the body reference coordinate system into account, then the 2x2 rotation matrix, vector u bar that is given in this example, and I'm going to get the vector of 2 components. Now these 2 components will be differentiated with respect to my variables that are same that in the previous case. It's going to give me mapping matrix, and again the dimension of the mapping matrix is 2 rows, 3 columns. Makes sense? Simple stuff. Not very difficult. Can-do attitude. Okay, so I have this mapping matrix, and then I'm going to go ahead and take my force and multiply that with my mapping matrix. It's going to give me, again, 3 components. Now, two forces are applying to single body. How can I summarize the effect? Well, simply summing up these 2 vectors because they are applying the same components. So here's my first, almost mistake. It's close. So here's my first vector, my second vector. When you do the math, this is how it reads. Now, how much they affect to my angle theta, my generalized coordinates theta? Well, if the body orientation is 45 degrees or 115 degrees, they will disappear. Because they're pointing in all the time in the same direction, and when exactly the body is in this orientation, they will eliminate themselves with respect to angle theta. Make sense? Beautiful. Now let's go back to this in-class quiz, and you need more time? Explanation of. Okay, so let me summarize the findings we have here. What was that, sir? You understood this, but you are worried about your fellow students. Yeah, I understand. Yeah, that's what I'm doing as well. So I'm not asking. I'm saying, Professor, can you repeat because I think that my fellow students, they don't understand. I figured out this already a while ago, but okay. Okay, but remember, if you are the one that is raising your hand and say, Aki, I don't understand. Was it lunch? Dinner? Okay, now let's look at this. So again, what is this third component? That third component is actually accounting, how far off is the force applying with respect to body coordinate system, and how much is a moment arm with respect to that. So it's kind of like it's moment that is applying to that system. That is applying the moment to our angle theta. Why is that? Because we really wanted to explicitly staying on tennorized coordinates, because we would like to solve Rx, Ry, and angle theta for every single body. That's exactly what we wanted to do. And that's what makes this automated system. All right? Make sense? Let me go and check this. Oh, we have more students now. So we have 89 students. So what is that? Oh, I know, but you need to know, you need to see the answers. These are the options. Now think about where the body reference coordinate system is located, how much this external force will introduce the moment arm to that. That's the key for success. But first, prior to that, think about how many components you have to have in your tennorized external applied forces. Now it's quite simple. So it's either 2 or 3 because those are the only choices. What coordinate system is having 2 components? Was it tennorized or global? Yeah, think about that. Okay? All right, so how is the success rate? Not 100, I can tell you that. For sure it's not going to be 100, but is it going to be more than 60? I don't know. It could be. It very well could be. Okay, so let's take, let me go here. Oh, here. Okay, some are still thinking, not many. So should I just go? So you guys are still entering your answer. How is aileron in up there? I think the up there is going to be fine. It's just a little problematic down here. So I have 84 answers already. You done? Not yet. Okay, I actually was thinking that maybe there is a way to make a little bit of competition here, like we can have different teams based on your nationalities, because we have this, what are the teams we have? We have German team, of course. What is another team? Was it the Iranian team? How is the team Russia doing? It's doing good. Yeah, I can see that it's doing really strong. Good. Is there something called Team Finland? Maybe. It's always up there. It's always in a back row. Always, always, always. Okay, so let me see. Okay, 2 students are missing. 1 is missing. I think that I'm good to go. Okay, and the success rate is 72. Oh, it was disappointingly low. Because okay, maybe it's not that bad, because if you're putting together 44 and 42, that's 86. Problem, of course, is that only 1 is correct. But it's telling you that you figured out how many components this vector must have. That's 3. 3. C and D options are no good. Absolutely no good, because they are missing 1 component. Okay, so let me go back here. No, not here, but here. So, how is that first option is correct? How can I know that the first option is correct? Yeah, well, because, look at this. Force is applying, force is applying in the origin of the body reference coordinate system. So what's going to be my level arm related to moment? 0. So that means that component must be equal to, my third component must be equal to 0. No other way. Okay? All right, so is 5 o'clock. Today you definitely need to have a break. Not because I think that you're still scoring really well, because this second in-class quiz was a little bit difficult. But now what follows is that, what we did in the past. Let me explain the big picture here, and then you will have your break. This is an equation that we're looking at. Oh, no. This is an equation that we're looking at when we're studying the dynamics. So according to this equation, it is saying that externally applied forces have to be equal than inertia forces. What is inertia forces? That is mass multiplied by acceleration. That is a force equal way than externally applied force. Those two forces have to be in balance. And if they are in balance, then you're going to have a dynamic equilibrium. So we wanted to express the dynamic equilibrium such the way that our unknowns, and again, what are our unknowns? Those are generalized coordinates. Vector Q is explicitly mentioned. How we did that in the first part, that is associated with this externally applied forces. So we did that by converting the force to be expressed by using generalized coordinates. Now, if you look at the inertia forces, how is it expressed here? What is a coordinate system that I'm using to express my inertia forces? What is my coordinate that I'm using to express my acceleration? Global or generalized? Global. It's global coordinate system. So now what I need to do is that I need to do this exactly same procedure, but for inertia forces. Remember the D'Alembert equation? So D'Alembert was able to express this equation like this. And that's it. So now the big discovery behind of this is not moving inertia forces from right-hand side of the equation to be in the left-hand side of the equation, because that's not that much in my mind. But inertia forces can be treated exactly same manner than externally applied forces. That's it. Let's make it happen. So let's treat them exactly same way. So what is that we need to do? Well, we need to look how is this force multiplied by virtual displacement. And what is that we're going to get as a result of that? We will get generalized inertia forces. And in generalized inertia forces, the unknowns are explicitly expressed. And unknowns are generalized coordinates. Make sense? Think about it. Think about that next, let me say, how much time you need, because next stuff that is coming is very, very painful. It's like super painful. Just to give you a little bit of like taste what comes, it's like this. Ooh. Oh God, it's like, really? But yes, really, that's what I'm gonna do. So how much time you need to recover? Must be less than a week. Is it 10 minutes all right? 10 minutes. I'm going to close my recording. I'm going to close streaming. 10 minutes. And then the painful part will get started. But the good news is this. That's it. Then we are ready to express the equation of motion. Okay.